All right, hi everyone. So yeah, I'm gonna give a 30-minute talk about building and scaling LLM Inference on Kubernetes. Um, who here knows what is an LLM? Everyone should maybe raise their hands right now up. But yeah, let's get into it. So, bit about me at the start. So basically, I have been a co-founder in multiple startups, and I have been practicing with Kubernetes for past 4 years or so. So not as deep into it as some other people here, for sure, but I have had great experiences with it. And actually, the reason why I started to look into Kubernetes was that one of my startups, like 5 years ago, ran into this issue that we used a lot of AWS services, and at some point we were like, hey, the costs here are quite high, what can we do? And then we are vendor locked and we can do nothing. All right, bit about the company. I don't know if it's actually allowed to tell about the company. Here you can remove it from the YouTube video if needed. But yeah, the reason why I'm talking about LLMs is that because the company that I currently work in and co-founded is building a platform that allows you to deploy these different open source LLMs. And the kind of core idea, why would you deploy an LLM inside Kubernetes, is that instead of bringing your data to these third-party black box services that can change internally, you want to host the LLM yourself and then integrate directly with that, and you don't need to worry about where your data is going to. All right, bit about the agenda for today. So first, some basic info about LLM Inference. And then I will show like a practical demo of deploying an LLM inside Kubernetes. And then I will talk about some problems that I've experienced in ConfidentialMind through our journey related to LLM deployments. All right, let's start with the basics. Everyone raised their hands on what is an LLM, so maybe this slide is not even needed. But basically, you can give text to an LLM and it will continue it. Also, you can give like chat discussions to it and it will continue it. And maybe the highlight from this kind of slide is that the open source community for open weight LLMs and open source LLMs is catching up with the private models quite nicely. It's kind of a cat and mouse game, but it's not that far off, especially if you bring the right data with the requests to the LLM when users ask questions. All right, so what are the actual differences with LLM deployments, so large language model deployments, compared to like your traditional workloads? So first of all, there is an extremely high demand for GPU VRAM. So even the smallest models that can basically not do too much for you, they will demand like tens of gigabytes. And any reasonable model will go up to like 60, 70, 80 gigabytes of VRAM memory. And that's just to get it running. Then of course, when you send requests there, it goes up in the VRAM usage. And compared to some other like scientific computation or so on, where we see like high VRAM usage, these are long-lasting workloads. So you basically want to have your API service running 24/7 instead of it being like some kind of a cron job that you run and reserve that VRAM for that time. Yeah, and also the CPU and RAM usage is widely different. You can see in the picture I have highlighted some of the deployments in one of our test clusters, and you can see the numbers on the right on the highlighted ones, which are LLM deployments. They are quite different from the other workloads. So what are the challenges that we face when deploying LLMs on top of Kubernetes? Well, first of all, you need the GPU compute. And the GPU compute is not exposed as a default to your containers. And overall, it's not seen as similar to like your normal RAM, for example, the VRAM in the GPU, because it's under that device. So most of these operators that expose the GPU compute to your containers, they actually say, hey, here is one resource, one GPU, two GPUs, three GPUs. So it's completely different from how you normally allocate CPU and RAM memory. But yeah, so you need some specific tooling to first of all expose the GPUs, and then you have all these issues with the scheduling and so on, because it's not like a normal CPU or RAM resource. And then the model weights, for example, are huge, so you need to have systems to cache the model weights and so on, and they are not pre-bundled in the container. And then the biggest problem of all, costs for running VLMs, not VLMs, LLMs, they are not trivial. So even like a basic A100 in Azure, it will cost you thousands per month. And you can run basically for a very limited amount of people, like model inference with that. And this is kind of the situation I see in different companies right now. And so there is like the AI visions and the ideas, and there is knowledge that, hey, we might need to run these models locally because we don't want to push our data there. But then the kind of the budget that they have reserved for that might not match the kind of visions they had. All right. So that was the basic intro to LLMs, and now we move to building an actual inference stack, so running an LLM inside Kubernetes. So yeah, the first part is that you need to, of course, expose the GPUs to the containers that then use CUDA or other to do the computation. And both NVIDIA and AMD offer their own operator that basically installs then a lot of things, even drivers on the nodes, to allow you to expose the GPU compute to the containers. And kind of nicely for us developers, if you just use one of these operators, you get this resource definitions. So the nodes will say, hey, I have 2 GPUs, and then you can target those nodes by saying, I need 2 GPUs here, and then it will be scheduled to a node that has 2 GPUs. So it seems like on surface very simple. Install this operator, and then just run your container. And this is the same slide for AMD. Looks pretty similar because the process is basically the same. Although I have to say it's a bit more complicated in our experience to use the AMD operator than our colleague there is laughing because he knows the pain very well. All right, so some core differences between NVIDIA and AMD. The NVIDIA software stack, for example, the operator, is much more advanced. It has been there for a longer time. It works well with different tools like VLM that I will talk about soon. And the GPU availability, for example, in public and private clouds, it's greater for NVIDIA. And then with AMD, I think it has one huge benefit. The GPUs are cheaper. So you can get much more VRAM on the AMD side with the same price. And these models need huge amount of VRAM just to run. So that's gonna be most likely where we see some future direction for how you run your inference. I know a lot of private clouds are now looking into buying AMD GPUs because of that. All right, so at this point now you have installed an NVIDIA operator or the AMD operator, so you can run containers that get access to the GPU. Of course, then you need a container that actually runs the model. For that, we use VLLM. It's a great open source project. Basically, it allows you to just say, hey, I want to run this model from Hugging Face. It will go and download that model, and then it offers an OpenAI style API to discuss with the model. So very straightforward. And it supports a lot of different models, like directly from Hugging Face. You don't need to do any specific configuration or so on. Here are some like actual arguments and other configurations that is good to take into account when you do your, for example, VLLM deployment. So first of all, they offer you arguments for controlling how much VRAM memory this specific deployment takes. And you can also, for example, control the max model length, which like controls how many tokens you can send to the model. That allows you to control a bit that how much of the free memory after the model weights you can still kind of have multiple requests reserving that if you control the max length of one request. Then most of the nodes that you will have in your cluster, they most likely will have multiple GPUs on one node. That's because like a very typical node or GPU can have 80 gigabytes of VRAM. And for example, you can run a model that needs 120 gigabytes. So in that case, you want to deploy it to a node that has 2 GPUs and split the model on the GPUs. And for that, the parameter is tensor parallel size, and you set how many GPUs you want to reserve for the process. There is also an environment variable that you can use to control which are the available GPUs for this process, or which GPUs based on the ID the process will take. And then you have the model cache that I already mentioned, which is very important because the model size can be huge. So you want to have a persistent volume claim, you want to mount that to the deployment, and then you want to say to VLLM that, hey, save the model files here. And that also means that if you are replicating, for example, the container, it will take the model cache from that same directory, so it doesn't need to reload it from Hugging Face. All right. Now I would have a demo, but we just edited my screen settings, so let's see if I can somehow get the right. Okay, is this more complicated than? Okay. Do you see my full screen now? Yes, good. All right, so I gave some basic information of how to deploy a VLLM inside Kubernetes and what to take into an account. And I can show you what does actually practically mean in one of our demo clusters. So in this specific demo cluster, we have 3 nodes. Each node has 2 GPUs. And for example, they are NVIDIA GPUs. So for example, if I describe one node, I can see that it here says, for example, this nvidia.com/GPU2. And I can see also lot of other labels on what is the specific GPU. And so on these labels you could also use to target, for example, the deployments to certain types of GPUs if you have multiple GPU node pools with different kind of brands in. And this is what NVIDIA operator, when you install it, gives you out of the box. So yeah, now my pods can get access to the GPU. And then if we go to check K9S, it seems I have internet connectivity issues because it should show me the resources a bit easier. Broken pipe. Okay, let's see if we get this going. All right, now we can see actually some deployments. And we have, for example, here an LLM deployment. You can see it's using a VLLM image. If I describe it, we can go a bit down to see what kind of parameters we have set for it. So you can see, for example, that this deployment, it has persistent volume claim mounted to a certain path that we also then say as a parameter here. This is a Llama 3.3 model specifically, and yeah, you can see it's taking 95% of the one specific GPU that is currently assigned to. And this actually says that it will be the index number 1 GPU on that specific node that it has been deployed to. And all this allows me to, now that I have the model deployed, and I have created with Istio a virtual service for it and JVT-based authentication, and since VLLM uses OpenAI style like API interface, I can now use an OpenAI library. For example, here is a simple Python script that just sends request to the service with the URL and API key, and it's currently asking, can you write a haiku about LLM inference inside Kubernetes? And if I run this, the model is now talking to me. LLM in the cloud, Kubernetes makes it work. Smartness scales with ease. Very nice. What's the time currently? Okay, I'm still nicely on time. And the OpenAI readiness also means you can use any other existing open source tooling, like OpenWeb UI, to talk to the models. So one of the models in this system is Gemma 3, which is a good multimodal model. So I could ask, this is an open source UI project that talks with OpenAI API, and I have pointed it to that model deployment. And now I can ask, voitko kertoa 5 asiaa Suomesta? So can you tell me 5 things about Finland? And as you see, this specific model can even talk to me in Finnish. So not that different from ChatGPT in a sense. All right. Guess that starts it from the start. Let's go to the right slide. Okay, so far everything seems really simple. You install this operator, and then you just run VLLM there, and you're done. But actually, no. So this is where the actual struggle starts. Now you have went through the basic starting guide on NVIDIA operator and VLLM. You get something running. You get some requests into it. So next I will go to some actual problems that we have seen in the field. Let's start with the first one. So basically, a lot of companies right now in Europe, for example, they are kind of early in their AI journey. And that means they are looking for a proof of concept type of thing with not a great budget. So the VRAM, amount of VRAM you will have in your cluster will be very limited. For this, what we specifically do is that instead of reserving one GPU fully for a model, we use the parameters in VLLM to reserve, for example, 80% for a bigger LLM, and then let's say 10% if we have an embedding model or something next to it. That's a way how we can run with even single GPU, like both the LLM model and then other models that are needed for normal AI systems. And these are basically similar arguments that you have already seen. So basically the memory utilization. And then crucially, instead of using the, hey, I need one GPU, you target the deployment to a specific pod, for example. We use the host header, so we can do very granular control over. I want to deploy this model, split it to the 2 GPUs on this node, and then I still have a space for a couple of smaller models on the GPU. And with these parameters, I can target and make a deployment that still works, at least for a low amount of people who are testing the system. This is actually a picture from our tool, but it kind of nicely highlights the fact that, for example, in the node 1 there, we have 2 models. We have Llama 3.3, Qwen 2.5, and then we have an embedding and a re-ranking model just on one node that has 2 GPUs. So that's a very like a normal configuration you aim for if you are building AI systems and you have limited amount of VRAM. Okay, next, observability. So naturally, you want to have some observability into what kind of GPU compute is currently used, how much VRAM memory is actually reserved by the deployments. And for that, since this is kind of a new thing, the whole GPU stuff, we once again see that the kind of out-of-the-box support in Kubernetes is non-existing. Luckily, NVIDIA, for example, has done their own tool for it. They call it NVIDIA DCGM. But for example, what we found out is that that only works if you specifically use that the resource that I reserve one GPU. So for us, for example, for the POC type of environments, it wasn't suitable because we wanted to have multiple models running. Also, this NVIDIA tool, it of course doesn't support AMD. So we actually started our own open source project just focusing on this specific issue of GPU workload observability. And it currently works with NVIDIA, and AMD support is coming soon. So if you need to deploy some LLMs and you run into the same issue, you can check this project out and even contribute if you want to. AMD support is coming soon. We just got the AMD test cluster, so we are going to work on that. The idea with this specific tool is that you can deploy it as a daemon set. It will go to every node, and it will use the tools on the node to associate different pods that are reserving the VRAM, and then you can scrape it to Prometheus or any other tool you use for observability. All right, and then last problem that I'm going to introduce here is scaling, and naturally this falls into the same issue as everything else, so this is new stuff, and since it's different, like the GPUs are different from how do we handle normally a CPU and RAM based scalability, there isn't like any good tooling for this right now. But you can still manually kind of try to make scaling happen. So basically for bots, you can use any metrics tool, for example, our Purple Pill, and configure it so that when the GPU compute usage metrics go this high, then replicate the deployment. And then for the cluster scaling, this is kind of I haven't seen any like production clusters yet that would actually add new GPUs in when there is high load. But of course, this should be possible if you use the GPU basically reservation. So you reserve one GPU per deployment. And then when you run out of available nodes, your deployment cannot replicate more, so the pod cannot scale. And then if you have configured that in that situation, for example, in Azure or AWS, you will add an automatically new node to the node pool. Then you get scaling that way also. Here is some examples on the code side, but I guess it's kind of visible, and we are running out of time, so I'll move to the next slide. All right, so to recap, so the LLM inference requires unique resources, not standard in your normal Kubernetes deployments. The GPU memory, it's kind of primary constraint, because without having enough GPU memory, you cannot even deploy the models. But we also see that the compute can become a constraint, especially when you are building actual AI systems like RAG systems, where you are sending a huge amount of requests to, for example, re-ranking model. And then kind of custom solutions are needed to kind of patch this whole thing together. Although there is some nice movement on open source projects that would abstract this whole set of things that I just was talking about. I think there is talk of about Ray, for example. So you can go check that out if you want to kind of dive deeper into that. And I think as a last kind of reminder, the whole space is moving really fast. So whatever I talked about today is most likely redundant like in 2 weeks or 3 weeks. So you really need to follow the space and adapt as you go. All right, thank you. Hopefully you got something out of it, out of this. And then if there is any questions, we can go over a couple. I think there is still a couple of minutes.
3 minutes.
Okay. Okay.
So like the acquisition time and like how you come by the GPUs, do you find that easier than NVIDIA? So it's the same, or it's just the price that makes difference nowadays?
Was it AMD versus NVIDIA?
Yeah, like
And
in price, but also like how easy it is to get a hold of them, and so if that's still a thing.
I think it's still a bit of a thing, although having GPU compute, for example, in Azure in Europe is quite hard on its own. We have, for example, one big client that uses Azure and AWS heavily, but they still couldn't get even one 8x NVIDIA system deployed. So yeah, AMD is catching up. NVIDIA is easier to get right now, especially in the private cloud, but yeah, both of those can have issues in you getting a Lines node, especially when we go to 8x or so. All right, there.
You got any experience in working GPUs?
With what? No. But I think it should be also possible. Yeah. I don't have personal experience, but I know it's possible.
And you can buy them only from Google. That's a limiting factor.
That's a small limiting factor, but if they are nicely available with good price, then why not?
Yeah, I was going to ask, have you had experience of deploying multiple instances of the LLM on one Kubernetes cluster to basically solve the customer side? And if you have had, for example, maybe thousands or even hundreds of thousands of requests, how you will handle the buffering or some kind of tuning mechanism so that there won't be timeout issues, or you are sending everyone maybe it can be delayed, but basically handling all the requests.
Yeah, well, of course, when you hit a certain limit, you cannot handle that situation. We had one project where we kind of implement our own queue, but for that project, the response time wasn't an issue. So like 1 minute response time was okay. But of course, there is no magical way around it other than running your cluster somewhere where you can theoretically add more GPU resources if needed. But VLLM has its own system. I think it doesn't automatically just start to error requests that are out of, when it's out of capacity, so to say, VRAM-wise or compute-wise. Was there still a question somewhere?
Yeah, this might be a long one. But the question about the sharing, you said that if you have a node with 2 GPUs and then you have 3 workloads like the VLM and re-ranking and embedding, those are 3 pods, each requesting 1 GPU. So how can you fit 3 pods to 2 nodes? How can they share?
Okay. So the question was about how can we deploy multiple models to the same GPU or one node that has multiple GPUs. And the trick there is that we just don't use the NVIDIA resource 1 GPU. We target to that node, and the containers will still get access to the GPUs. And then with the parameters on VLLM or the other containers that we use to run it, we request a certain amount of VRAM for that process. Of course, that's not like necessarily a production level setup because it can get out of hand maybe, but But at least, yes, but VLLM is pretty good in like, if you say that takes 60% of the VRAM, then it kind of stays on that. It goes a bit over for some reason, but about
Techniques like GPU time sharing and GPU slicing.
Yeah, but you mentioned that I mean, that would have been the next question, but you said that you're just using 4 GPUs.
yeah, but
you don't use the resources to
yeah.
schedule. You use the host name to schedule it, and you know that I can
Yeah.
do this.
Yeah. So we have kind of resolved that situation by when you make the deployment, we warn you if it's going to be an issue. But as was said here, MIG is, for example, very good on NVIDIA side. We don't use that because it requires specific GPUs, and we want to keep it open for more. But there is nothing limiting you from using that when you make a deployment, and you want to isolate the workloads that way. But yeah, for a production level setup, something like MIG is for sure better.